All right, the second lesson of tonight's combo platter, 13.3, fluids at rest and motion. We just got done talking about the vocabulary part of fluids at rest and motion. Now we're going to talk about the mathematical part. And there are a few handful of equations that come with fluids when we talk about fluids at rest and fluids in motion. Fluids at rest, we are going to have Pascal's Principle. What is Pascal's Principle? Pascal's Principle essentially says that pressure in fluids depends on their depth. Which, think about it, the further you swim down in the ocean, what happens to the pressure the further you swim down in the water? You have more weight on top of you, therefore you have more force on the same amount of area, so your pressure is going to increase. Pascal's Principle. Any change in pressure is applied to a point that's transmitted throughout the fluid. So anytime I'm changing pressure, that's applied throughout the fluid. A great example of Pascal's Principle is hydraulics, which you can think about on page 352. You have fluid connected in two chambers. Again, we're going to use pressure is equal to force, excuse me, force divided by area. So pressure is equal to force divided by area. One can figure out the force. When we have hydraulics, typically what we have is we have one tube that's very narrow, and we have one tube that's very wide. And what we can do with that is we can take pressure or force and apply it, a small amount of force here, and a large amount of force will be equally distributed throughout the fluid on the other end. So when we use the pressure equation, force is equal, or pressure is equal to force divided by area, our hydraulic lift equation is F2 is equal to F1 divided by A2. F being force and A being area. Again, remember force is in newtons and area is in meters squared since we're dealing with the metric system. So that is the first equation that you'll get. F2 is equal to F1 times A2 over A1. Next up, we're going to talk about being in a fluid. What happens to you when you are in a fluid? As you go deeper, we've already talked about this, as you go deeper in a fluid, there's more pressure because you have more water, or you have more pressure, or excuse me, you have more weight, or you have more force on top of you. So, what is the equation for pressure of a fluid on your body? Well, first things first, that guy right there, who I just highlighted green, that's a free diver. That guy dove 108 meters on his own. That's a world record. What type of pressure was he feeling on his body? Pressure, capital P, is equal to pHg. What is P? P is the density of the fluid. I can't say that enough. It's the density of the fluid. So make sure you have that down. It's the density of the fluid. Capital P is pressure, lowercase p is density, h is the height at which you're in that fluid, and g is gravity. So P is equal to pHg. So we have our hydraulics equation. Now we have our pressure or equation of being in a fluid. When you are also in a fluid, you experience buoyancy. What is buoyancy? Well, when you think of buoyancy, it's probably the idea of that you're going to bob up and down in the water. And that's kind of true, but buoyancy is really liquids creating an upward force on the object that it's in, the object in it. So it's the upward force created with increased pressure with increasing depth. So you are going to have the idea to bob. So it's going to be the force applied by a liquid is really the buoyant force. Think about it. When you're swimming, typically you feel lighter when you are swimming than you are walking on land. Why is that? Because the buoyant force is canceling out some of your actual weight and you are feeling slightly lighter. And that's called your apparent weight, and we'll talk about that a little later down the slide. When we talk about the equation for the force of buoyancy, how much is this fluid pushing me up? Well, F of buoyancy is equal to the density of the fluid times the volume times gravity. And actually, I jumped the gun here. If you go back to this slide, I messed up. That's the density of the object in this example. So it's not the density of the fluid in the pHg equation, it's the density of the object. But when we were talking about buoyancy, it is the density of the fluid. I apologize for that mistake. So force of buoyancy is equal to P fluid Vg. P is the density of the fluid, V is volume, G is gravity. Now when we are talking volume, or not volume, density, what is the volume, excuse me, gosh, what is the density of water? For our intensive purposes, it's 1,000 kilograms per meter cubed. Now, you may be used to that in chemistry as 1 gram per milliliter cubed, and they are the same, but since we are dealing in kilograms in physics most of the time, it's 1,000 kilograms per meter cubed. Archimedes' principle also applies to buoyancy. And Archimedes' principle explains an object immersed in a fluid has an upward force on it that is equal to the weight of the fluid displaced by the object. Essentially, this explains floating objects. How do things float? Why do ships sail? Have to deal with Archimedes' principle. If the weight of the boat is equal to the weight it displaces, or less than that, it's going to float. So sink or float is simply determined by the difference between the buoyant force and the object's weight. And that is the apparent weight. Now, I don't have this equation in here, but it might be important to have. Apparent force, your apparent force is equal to the force of weight minus the force of your buoyancy. So something to have in mind there. So the apparent force is equal to the force of weight minus the force of buoyancy. So you've gotten 3 equations so far. The hydraulics equation, the amount of pressure from being in a fluid, and now the amount of force created by the buoyant force while you're in a fluid. So if we look at an example here, we have a cubic decimeter, which is 1.0 times 10 to the third negative 3 meters cubed. You can thank me since I helped convert that already, of granite. Building block is submerged in water. The density of granite is 2.7 times 10 to the third kilograms per meter cubed. What is the buoyant force acting on the block? Well, we know, and we've talked about this, the buoyant force is equal to the density of the fluid times the volume times gravity. What is the density of water? We just talked about it. The density of the fluid is 1,000. Our volume of our cube is 1.0 times 10 to the negative 3. And gravity is always a constant at 9.8. So we go ahead and we plug this in. Our buoyant force is equal to 1,000 times 1.0 times 10 to the negative 3 times 9.8. And we end up with our buoyant force, using significant figures, ends up being 9.80 newtons. So that one was pretty easy. The second part of this question is, what is the apparent weight of the block? Now remember, the force, or the apparent weight, the apparent force, is equal to the force of the weight minus the force of buoyancy. Well, we have the force of buoyancy. The force of buoyancy is 9.8. How are we going to solve for the force of weight? Well, we have to go back here. Density is equal to mass divided by volume. Density is equal to mass divided by volume. The question tells us the density of granite. The density of granite is 2.70 times 10 to the third. We don't know the mass, but we know the volume is 1.00 times 10 to the negative 3. When you do that, your mass ends up being 2.7 kilograms. How do we convert kilograms to newtons? We're going to take 2.7 and multiply it by 9.8. When we take 2.7 and multiply it by 9.8, we end up getting, I think, 17 something. Oh, 19.6. So now, let's plug in our numbers. Our weight is 19.6 newtons minus our buoyant force, which is 9.8. We're going to take 19.6 19.6 minus 9.8, and our apparent force is 9.8 newtons as well. So the block actually weighs 19.6 newtons, but it feels like it's only 9.8 because of the fluid of that buoyant force. The fluid is pushing it upward. So here's kind of one of the examples that you'll have to do in the problems in the book tomorrow in class. But we have one slide to go, and that last slide has to deal with Bernoulli's principle. We've talked about hydraulics, we've talked about Pascal's principle, we've talked about Aristotle, and now we're talking about Bernoulli's principle. It's going to be good to know these three principles. So I highlighted the first one actually on the first page, Pascal's principle. The second one, which would be good to know as you go back through your notes, is Archimedes' principle, explaining how things float. The last one, which we are going to talk about, is Bernoulli's principle. And Bernoulli's principle says as the velocity of a fluid increases, the pressure exerted by that fluid decreases. Now, have you ever had the shower curtain stick to you in the shower? And what I mean by that is you've been showering, does it feel like the shower curtain's pushing in on you? Well, why does that happen? Think about it. Usually in the shower you have warm air. Warm air is going to be traveling slightly faster than the cool, stationary room temperature air around it. That air or that fluid, the water, is going to be moving faster. So in the shower, all right, here's my shower. I'm standing in my shower. The fluid is moving. Outside of that, I've decreased the pressure. Well, outside of that means I have higher pressure, which means that higher pressure is pushing in on me, which is going to push the shower curtain in. Or if you've ever been driving on the interstate, or not even interstate, a two-lane highway, and you pass a semi. That semi is moving more air than you because it's larger. So what happens is, here's your car. You have lower pressure where the car is driving, right? And typically higher pressure on the outside. The fluid between them is going to be low. So what happens is the higher pressure outside, where it's not moving at all on the highway, is going to push you or feel to suck you into that car. So that is Bernoulli's principle. Now, where are some examples where Bernoulli's principle comes into play? We have blood circulation, paint sprayers, perfume bottles, automobile and aircraft, streamline flow around objects. This is how a plane flies. Think about it. A wing is cut like this. Right? Air underneath is going to go slower than air over the top of the wing. If the air over the top of the wing is going slightly faster, your pressure is going to be less on top, more on the bottom, and this pressure is going to give you a small amount of lift, and that's kind of the idea of how an airplane works. So outside of mathematical equations, we have three things we need to hammer home with this. Outside of the equations, we have Bernoulli's principle, we have Archimedes' principle, and we have Pascal's principle. You're going to have to know those three and be able to do the math questions, which we will do in class tomorrow.